I will talk about superstripes and quasicrystals with the soft corona interactions. So just not to be misunderstood, this corona that I'm talking about has nothing to do with the coronavirus. So you will see in a moment why I'm talking about hard soft corona interactions. And this work, actually, the presentation is based mostly on a recent work that we submitted together with Bruno Abreu, who was previously a PhD student at Unicampi, and now he moved. He was for a short period also a postdoc in my group, and now he moved to the US. And Fabio Cinti, who is now a professor at the University of Florence in Italy. Before starting, let me just advertise the place where I work and where I live, which is the Federal University of Rio Grande do Norte, which is located at the city of Natal in the northeast of Brazil. This is a postcard of the city of Natal. This is the so-called neighborhood of Ponta Negra, which is the most touristic place of the city, and the university is located just 4 or 5 kilometers from this touristic point. At the moment, we have 2 postdocs, Diego Paiva, who was also a PhD there in São Carlos, Arsenio, who spent a year in Sweden with the joint project between CAPES and the Swedish Academy of Science. And then we have 3 PhD students, Igor, Heitor, and Lucas, 1 master, Natani, and 3 graduates. At the moment, we are mostly interested in problems related to, to applications of ultracold atomic systems, with a specific reference to strongly interacting many-body system, exotic phases with Bose-Einstein condensates, applications to quantum metrology and quantum sensing, and in general, a quantum simulation also of relativistic models. We are also quite active in the organization of programs and events. So at the moment, we should be holding this program on frontiers of quantum simulation with synthetic systems, which has been postponed to the next year, hopefully, in collaboration with Leonardo Fallani, Mohamed Hafezi, and Christiane Morais-Smith. And in 2022, we will have another workshop on patterns and tangles in hard and soft condensed matter systems. And of course, as probably some of you know, last year we also organized with Roman a workshop on systems with long-range interactions, both on the classical and quantum side. So, of course, you're all invited to join us, to visit us, and also to collaborate with us if you think that you are interested in the things that we do. And please feel free to get in touch with me at any moment by email, or even we can discuss on Skype, on Zoom, or Google Meet at any moment. Okay, let's now move up to physics. And I think that actually the general framework that is on which this presentation is based is the problem of crystallization in ultra-cold atomic systems. For the purpose of this talk, by crystallization, I mean the self-ordering of particles into an array with regular geometry. And I will be more specific during the talk on this particular definition. The first and prototypical example of crystallization in the quantum case, in quantum systems, was first proposed by Eugene Wigner back in 1934, who considered the physics of an electron gas in a uniform positively charged background. In this particular case, the type of interaction between the particles is a Coulomb interaction that can be either repulsive between electrons or attractive between electrons and ions. So the problem that Wigner wanted to understand more in detail was the possibility of having a transition between what we would call today a liquid electronic state into a crystalline state, or within the modern technology, a Wigner crystal or a Wigner solid. Now, it turns out that if one wants to understand the physics of Wigner crystallization, one has to compare the typical energy scales involved in the problem. So here, for example, we have two types of energy scales. One is the kinetic energy, the other one is the interaction energy. The kinetic energy scales like the inverse of the interparticle or average interparticle distance squared, because the kinetic energy term is proportional to h bar square over 2m times the gradient, the square of the nabla squared of the wave function. The other term is the interaction term, which here scales like 1 over the average interparticle distance, since we are talking about Coulomb interaction. So it turns out that when the system is in very high densities, then it prefers to be in a lead state because kinetic energy dominates. On the other hand, when the interaction dominates, so when we are at low densities, then the system prefers to find itself into a crystalline state. Now, this physics of crystallization has been suffered a very, of course, very many investigations, very many studies during the past decades, and it was somewhat recovered, or it was fashionable again over the past 15 to 20 years, mainly due to the possibility of simulating this physics in the context of ultracold gases. Now, there are several possibilities to study crystallization in such setups. For example, by using long-range interactions, like for polar molecules, magnetic atoms, or Rydberg atoms that I will mention in a moment, which are all neutral systems. One can put atoms in cavities, or use ions, which have positive charge, or spin-orbit coupled Bose-Einstein condensates. And there have been associated to each kind of platform many experiments over the past few years. As I just said, one possibility is given by Rydberg atoms that display very specific and peculiar properties, like, for example, the fact that they show a sort of hydrogen-like wave function, in the sense that basically a Rydberg atom can be considered as a sort of hydrogen atom where the electron in the external shell can be excited to a state with a very high principal quantum number. In terms of being more quantitative, one can study, for example, the scaling of the energy of the electronic states and find that indeed it follows the same scaling of the hydrogen atom, apart from a small quantity which is called the quantum defect, this delta Lj in the denominator of the Rydberg formula, that is typically of order 1. And it might depend on the orbital quantum number L and the total angular momentum J. The radius also scales like, in the case of the hydrogen atom, like n squared. This n star means simply n minus delta Lj. The lifetime of these excited states scales like n cube. And the most important thing probably is that the van der Waals coefficient that rules the strength of the interactions between two atoms that are excited to Rydberg states can scale like n to the 11th power. So it can be very, very strong if one excites the electron of these Rydberg atoms to very high principal quantum numbers. The other important thing about Rydberg atoms is the fact that one can realize very different and very broad class of interaction potentials. One, for example, realize van der Waals interactions when typically the states to which the electron is excited are not resonant with the other electronic states. One can, for example, obtain or mimic the physics of Forster resonances that are a very useful tool to describe energy transfer even in biological systems, like, for example, in photosynthesis. Or, for example, resonant dipole-dipole interactions that are useful to make quantum simulations of magnetic systems due to these flip-flop interactions that are shown schematically here in this graph. Another possibility is to use the so-called Rydberg dressing that consists into a far-off resonant excitation to Rydberg states And as I will discuss in a minute, will allow also not only to change the strength of the interactions between the Rydberg atoms, but also the shape. Then there are several, this field of Rydberg atoms essentially exploded over the past few years. And as you can see, there are very many reviews that these are just the ones that I found recently on this field. And there are nowadays applications not only to quantum simulation, which is more or less the area in which I wanted to focus this presentation, but also applications to quantum metrology or to quantum information and realization in general of quantum gates. So let me start by focusing a little bit more on a specific class of problems that we wanted to investigate. So one important thing that we have to consider when we want to address this problem of crystallization is what kind of tools we have at our disposal in order for particles to crystallize. Of course, it is important that particles are interacting. Otherwise, of course, we have just a system of free particles that would just occupy uniformly our 1D, 2D, or three-dimensional system. So the simplest type of interaction that we can envision between quantum particles is certainly the case of an hardcore potential, which basically consists of a sort of infinite repulsive well with the radius or with the width of the order of sigma 0, which is essentially the radius of this infinite repulsive barrier. So it turns out that if we are at very low densities, then the system is indeed a fluid. Particles occupy the space uniformly, and one can compute, for example, the so-called equation of state as a function of the width of this repulsive potential. And it turns out that it follows this this equation. So this is just the energy per energy per particle of a two-dimensional system of particles interacting of bosons interacting via this infinite repulsive barrier. And it turns out that, as you can see on the rightest part of the figure, essentially at some point this curve has to stop. And in this particular case, what I'm showing is the energy per particle, either from this equation found by Schick back in the 70s, and some recent Monte Carlo calculations done by Pilati, Giorgini, Prokofiev, and other collaborators back in 2005. So what happens when we go to very high densities? Well, the system prefers to crystallize in two dimensions. For example, the typical crystal is a triangular crystal with a single particle occupation, so a single site occupation. So every site is occupied at most by one particle, and it cannot be different than that just because there is this infinite repulsive potential, which has this width of radius sigma 0. Now, although it is a prototypical and very simple potential, of course, it is also very important for applications. For example, in the context of ultracold atomic gases, this is a very important model potential because this radius sigma 0, in the case of very low densities, when we talk about scattering processes between ultracold atoms, it is just represented by the so-called scattering length. So basically, although it is a very simplistic and elementary potential, it can indeed be used in order to simulate the physics, at least numerically, the physics of ultracold atomic particles. A second important example is the so-called soft core potential that can indeed be simulated via the so-called Rydberg dressing that I was mentioning before. The important feature here is the fact that, of course, again, this is a sort of idealized potential. The true potential has the shape which has a plateau for very small interparticle distances, and then it decays as a power law in this particular case as 1/r⁶, like Van der Waals potential, when the interparticle spacing is sufficiently large. Now, again, if you look at the physics at low densities, again, this potential can be represented effectively by a single parameter, which is the scattering length. So one would expect, again, to find the system in a superfluid phase with a uniform distribution of particles. So one can compute, for example, the superfluid fraction, which is equal to 1. But then again, the question is, what happens when we go to larger densities or to larger interaction strengths? So which means when we increase the height of this plateau of the soft core interaction. Well, it is quite interesting here because as we removed the hardcore constraint that we had in the infinite repulsive that I was mentioning before, indeed here clustering is possible. So one can form these clusters where each cluster has many particles inside that, and then the clusters by themselves are arranged in a so-called Wigner cluster crystal. So basically in 2 dimensions we will find clusters of particles where these clusters occupy the sites of a triangular geometry or triangular array. Now, if one goes to even larger larger densities of interactions, then one recovers essentially the physics of a classical cluster crystal. To make things a little bit more quantitative, one can look at the phase diagram in terms of the densities and this rescaled interaction strength, and one finds the superfluid phase at low density and low interactions, a classical cluster crystal when or normal solid at larger densities and interactions, and in between there is this stripe, this red stripe or red region that corresponds to a so-called supersolid cluster crystal. Now the word supersolidity here is very interesting because it just denotes the property of the solid that is able to break essentially spontaneously translational symmetry by creating these clusters that arrange regularly in space, but at the same time these clusters display superfluidity, which is basically the property of a substance to sustain persistent dissipation as flow. So basically this this can be translated into the fact that these particles that belong to each cluster can indeed tunnel between nearest neighbor clusters. There are in general different types of supersolidity. For example, at low densities, one can indeed find when in the regions closer to the commensurate occupation of these clusters to unit filling, which means that one has either 2 or 3 particles per cluster, a mechanism that is very similar to the one that was discussed at first by Andreev, Lifshitz, and Chester, which is the so-called defect-induced supersolidity. So in this particular case, the supersolid is induced by the delocalization of either vacancies or defects that are created on top of the commensurate lattice. On the other hand, at very much larger densities, one finds a different type of supersolidity, which is called a density wave supersolid, that can be nicely described by a sort of mean field approach, where basically the modulations in the density are responsible for the creation of a supersolid state. Why are these density modulations compatible with the supersolid? Well, the modulations in the density, like in this picture that we took from a Monte Carlo simulation, are responsible for the breaking on translational symmetry. On the other hand, the fact that the density in between the clusters is non-zero, it induces the tunneling, is responsible for the fact that the different clusters can indeed communicate among them, and then this induces a finite superfluid fraction. If one is interested into the microscopic mechanism that induces these density modulations, one has to rely on the interpretation of the so-called Roton mechanism that is related to the fact that excitations in the superfluid phase display a very similar spectrum that is also found in the case of superfluid helium, which is basically linear at very small k's, so at very small momenta, but then it has a maximum, which is called a maxon, and then a local minimum, which is called a roton. Now, when one tunes either the intensity of the interaction or the density, these two larger values, the gap or the height of the rotor minimum can indeed squeeze to zero, can vanish. And in that case, in that particular case, one would expect that excitations with either zero momentum or at finite momentum, which means essentially density modulations, can be created without any energy cost. So at some point, it becomes more favorable for the system to create density modulations than to stay in just a uniform, boring superfluid state. Okay, so this basically is the physics of the soft core. Let me mention that the physics of supersolidity can also be found in other types of systems, like, for example, dipolar systems, which have been quite heavily studied both theoretically and experimentally over the past 5 years. There are several experiments. The most important ones are with either dysprosium atoms in the group of Tilman Pfau in Stuttgart and in the group of Giovanni Modugno in Pisa. And the other one, very relevant experiment for the study of these density modulations, is the one in the group of Francesca Ferlaino in Innsbruck that considers a different type of dipolar systems, namely erbium atoms. Now, in this case, it is also interesting the fact that on top of the physics of these density modulations that induce the supersolid, there are also different, there is another kind of interesting phase, which is the one of quantum droplets that have been really heavily investigated, heavily studied over the past few years. And if you're interested, there is also a nice work that we have done, we published recently also in collaboration with Andre, where we were interested in the possibility of having a nice vortex states inside these droplets. The interesting point here is that for the polar systems, depending on the dimensionality, supersolid states can indeed appear or not. But this is really something that I would not like to spend too much time during this talk. But of course, if you're interested, just ask me either now or even after the talk. And I would like to also point to this nice recent review by the people in the group of Tilman Pfau that has been recently appeared in the archive. Let me now just move to the third type of example that I would like to mention, which is related indeed to the most recent work that I wanted to advertise today, which is the case of the so-called hard core and soft core, or to be more compact, hard soft corona interactions. Now, this potential here that you see in the bottom part of the slide is essentially a combination of the two previous model potentials that I was discussing before. So there is a hard core potential for distances between 0 and sigma 0, and a soft core potential between sigma 0 and sigma 1. Apparently, it is why should we study this potential? I mean, in principle, there should be some physics related to the hard core and some other physics or some other evidence related to the soft core potential. Well, indeed, it is partially true, but on the other hand, one can find very nice types of phases, even in the purely classical case, which actually gave us the inspiration to look a little bit more in detail on the quantum side of this problem. This physics of this hard-soft corona interaction has been explored since the beginning of the 2000s by several groups. So there was a Nature Materials paper in 2003 that basically was investigating the physics of this hard-soft corona interaction as a function of density. And one can indeed see that one can go from a so-called liquid phase at low densities to a higher density big crystalline phase, or a labyrinth phase, which basically represent these weak gold stripes, and finally at larger densities even to a so-called quasicrystalline state that I will discuss a little bit more in detail in a moment. It is interesting to mention that since then there have appeared many other works that try to characterize a little bit more in detail, in particular, the physics of these larger densities, which is the most interesting one. Like, for example, these people in Utrecht by Marjolaine Distra and by Primo Zierl and collaborator back in 2014, 2015. There is still a lot of attention to this classical problem nowadays. So it's really a very hot topic in the context of soft matter physics, where these kind of two-body interaction potentials are really important in order to model the interaction between polymers or even other kind of micelles or dendrites, which are more complicated kind of structures that appear actually very frequently in biophysics. Now, on the quantum side, I would like to first mention what these quasicrystals actually mean. So by quasicrystal, before talking about quasicrystal, we have to recall that in condensed matter, there is a very important theorem, which is called the crystallographic restriction theorem, that basically bounds or confines or limits the number of allowed symmetries in crystallography to either 2, 3, 4, or 6-fold symmetries. But there are other types of symmetries, therefore, that are not allowed, like, for example, the 5-fold or the 7-fold, or even higher types of symmetries are indeed forbidden. Now, this paradigm actually changed when Dan Shechtman and collaborators found back in the 80s that there was experimental evidence of structures with 5-fold symmetry. It was soon realized that those kind of experimental evidences were related to some other types of structures that were investigated a little bit before by people like Penrose, and were put in connection to the fact that different types of symmetries, if one relaxes some conditions in order to find perfect crystallographic symmetries, could be found indeed in nature. Now, in terms of physical systems, so on the quantum side now, recently appeared several types of proposals in order to simulate these quasicrystals in ultra-cold setups. Like, for example, there were some proposals to observe, actually these are theoretical proposals by Daimler and collaborators, or more recently by a group in Texas and also in China, to observe superfluid quasicrystal in Bose-Einstein condensates, either with dipolar interactions or with a complex Raman coupling between internal levels in a BEC. There are also some interesting experimental applications that have been realized by Ulrich Schneider in Cambridge and David Weld in Santa Barbara, where basically they apply an external quasicrystalline, either one-dimensional or two-dimensional potential, in order to observe a quasicrystalline pattern of particles. There is also another proposal to observe quasicrystalline states in cavities by the group of Helmut Rich, which was published recently in PRL. There are also other theoretical investigations that mainly pointed out at specific kind of two-body interaction potentials that allow the possibility of, the presence of quasicrystals in the phase diagram. And in particular, I want to mention this work by Guido Pupillo, Primo Zierl, and Fabio Cinti from the beginning of this year, where they consider these types of more complex or more complicated soft core interactions that are called, or they belong to a class which is called the Lifshitz-Petrick Gaussian potentials. So within this class of potential, one can indeed find these nice quasicrystalline patterns, which are of the type of cluster, like this, very similar to the ones that I was discussing in the context of pure soft core interactions. There is, however, the indication that these quasicrystalline structures are only stable in the context, at finite temperatures. Indeed, if one observes or one studies the phase diagram of an n-particle bosonic system interacting via this Lifshitz-Petrick potential, one finds that this red region corresponds to a quantum quasicrystal only appears at finite temperature. On the other hand, we were indeed stimulated and motivated by the fact or question of whether quasicrystalline states could be stabilized even in the ground state of an n-body system or many-body system. And to do so, we actually looked at this problem of the hard-soft corona interactions that I was already mentioned in the case of the classical soft metal systems by performing heavy path integral Monte Carlo simulations. So again, the interaction potential is specified by this very simple equation. So there is this hard core plus this soft potential when the interparticle distance varies between sigma 0 and sigma 1. So one has at our disposal different types of parameters that we can play with. So we have either the height of the potential, of the soft core potential, which is this epsilon. We have the ratio between the two radii of the hard-soft corona interaction. And of course, we have the density of the system. One can, for example, fix the ratio to a specific value, for example, 2.5, which corresponds to this phase diagram here on the rightest part of the slide, and try to map out the phase diagram. In this case, what we found is a sequence of transitions from a superfluid phase to a triangular crystal. Then there is some phase coexistence in between the triangular crystal and some stripe phase. Then these wiggled stripes or labyrinth phases, a kagome pattern, and then eventually a triangular crystal at very large densities. And this indeed is a sort of extended phase diagram with respect to the case of the soft core interaction potential and the hard core potential that would just correspond to the case where this epsilon is equal to 0. So when we look at the vertical part of this phase diagram, when epsilon is equal to 0, we indeed recover the phase diagram of a system of hard core particles. Now, of course, we can characterize a little bit more in detail these phases by looking at the radial distribution functions or plotting, for example, the density of actually the equilibrium density that appears from our Monte Carlo simulations. And also we can realize indeed that quantum fluctuations are relevant, because if we compare the density distribution for the case of classical quantum Monte Carlo simulations and in the case of quantum Monte Carlo, then we found that for some specific values of the parameters, the two types of configurations can indeed be different. So it turns out that when you lower the temperature below some certain critical value, then you can expect that the physics that you can simulate by just taking classical particles interacting by this hard core, soft core potential is different from the case of just quantum particles. Then one can look also at the superfluid properties, which is a genuine property of our bosonic system, and find that indeed between the triangular crystal, which is not superfluid, and the kagome lattice, there is a nice wide region of superfluid stripes that display anisotropic superfluidity, which means that typically one would expect more superfluid behavior along the direction of the stripes, where basically particles can essentially flow without any kind of friction. Whereas on the orthogonal direction to the stripes, where there are indeed these density modulations that give rise to these stripe patterns, then the superfluidity is indeed smaller. So for these particular simulations that I'm talking about, we have, for example, that the parallel superfluid fraction is equal to 0.7, whereas the orthogonal one is equal to 0.35, so essentially half than the case of the parallel superfluidity. If one, one can indeed characterize a little bit more this quantum property by looking at the permutation cycles between particles, which basically tells you qualitatively where basically you can essentially exchange particles between a large number of clusters within the system, which is indeed typical of the superfluid and supersolid stripes. Whereas if you look at the kagome or the triangular crystal, particles can only exchange, so this bosonic exchange, which is a genuine quantum property, can only take place within nearest neighbor particles. Then one can look at the, one can change the ratio. So of course, in principle, the parameter space is very wide, so one has to restrict to some specific parameter range. If we look still at the high density regime, but now for soft core to hard core radii ratio equal to 1.95, then we find that there is a very nice competition between two different types, actually three different types of particle arrangements. At relatively low interparticle densities, we found that the dominant structure is the one given by the triangular crystal, which is represented here by this black configuration. If one goes to larger densities, then this triangular crystal competes with the quasicrystalline arrangement of particles with a 12-fold symmetry. What do I mean by that? Well, if you look at either the snapshot of the coming from our path-integral Monte Carlo simulations, which is given by this green figure here in the top right part of the slide, and its Fourier transform, what you observe is that in particular the Fourier transform, you would observe that there are some dominant peaks, and if you count them, they display indeed 12 peaks, 12 bright peaks in Fourier transform, which is an indication of the fact that indeed we have a quasicrystal with 12-fold symmetry. How do we actually can be sure that, how can we be sure that it is indeed a 12-fold quasicrystal? Well, first of all, we have to compare the energy with the triangular crystal, first of all, but before that, actually, we have to construct a 12-fold quasicrystal and try to give it to our path-integral Monte Carlo simulation as a sort of input configuration, and then try to relax this configuration by letting the algorithm run. So we start with an algorithm to create this 12-fold quasicrystal, which was proposed by Henley back in 1993, which considers this structure of hexagons and dodecagons that basically fill the whole space. And then what we find is that what we do is that around each one of these blue dots, we create a dodecagon given by these red dots. And then what we do, we observe that if we want to create hexagons inside these, we want to fill the space in between the red and the blue dots with the hexagon, which compose indeed our lattice sites in the final particle arrangement. We have the possibility of actually creating a sort of random arrangement by considering two types of hexagons which are rotated by 30 degrees one with respect to the other. So if you just basically flip a coin and choose either the first or the second type of hexagon to fill the space in between the red dodecagons and the blue dots, one can find in general very different types of configurations. If one joins now the green dots, one finds that one can indeed tile, which means fill the plane, the two-dimensional plane, either with effectively triangles or squares. So this type of 12-fold quasicrystal is called in literature a random square triangle tiling of the two-dimensional plane. So this kind of 12-fold quasicrystal can be compared to simpler types of configurations that fill the plane continuously without any gap, but in a regular way, so in a periodic way. So the quasicrystal is quasi-periodic, so it is not periodic. But if you compare it with what is called the sigma phase, which is one type of phase that fill the plane periodically, but not with the same time of structure, like for example, either all triangles or all squares, then one finds that due to the geometric constraints and the fact that we are indeed simulating a finite system, the sigma phase dominates a little bit. But one has to also to recall that the sigma phase is a so-called periodic approximant of a 12-fold quasicrystal. So it means that if one indeed had an infinite system, the configuration that would dominate would be given by the 12-fold quasicrystal. And indeed, what we find is that if we go to larger interparticle, larger densities, indeed, this sigma phase and the quasicrystal dominate over the triangular crystal. Another important way to characterize these quasicrystalline phases is given by the so-called bond-orientational order, which is an order parameter that basically measures the angle between pairs of particles that fill the two-dimensional plane. So it turns out that the bond-orientational order associated to a triangular crystal is picked when to the case when nu, there's the integer associated to the specific bond-orientational order of the triangular crystal is equal to 6. Instead, the 12-fold crystal, 12-fold symmetric quasicrystal displays peaks to when nu is equal to 12. We can, of course, also try to compare these energies to the classical configurations, and one indeed finds that by just plugging the energy of a sigma phase, a quasicrystalline phase, and the triangular crystal at larger densities, the quasicrystal and the sigma phase are indeed display lower potential energy than the triangular crystalline configuration. So I'm heading towards the conclusions. So the message that I wanted to convey during this presentation is the fact that by looking at relatively simple toy model potentials, one can indeed find a relatively large number of interesting phases. In particular, what we found is that by combining the shapes of a very elementary hardcore potential and the softcore potential, which can be simulated by means of Rydberg dressing, one can find interesting superfluid stripes and quasicrystalline patterns. And the perspective, from my point of view, at least along the direction of the presentation that we had today, is of course a systematic characterization of the quantum phases with a more general non-local potential, or to extend these types of investigation even to fermionic system, and try to make some realistic proposals, of course, for the realization of these phases in AMO platforms. So with this, I would like to conclude and thank you for your attention. And I give back the word to Roman.
Sorry, thank you very much, Tommaso. Are there some questions?
So I do have some questions, Tommaso. Very nice. So what is the particular difficulty to consider, as you were mentioning, you can consider a power law potential, for instance. Why choosing this step-like potential? What I mean, it may be didactic. You may have like real systems that in approximation behave like that, but a power law potential would be more realistic, right? So what is the difficulty of taking that into account?
Well, I would say that depending on the power law of this potential, one may have to consider some specific numerical techniques in order to take into account to avoid the interaction between copies of the main system that you are considering. So I would say it's more numerical. So there is, first of all, there can be some numerical issues. If you want to simulate a dipolar system that we know much better, Andre, or even Coulomb interactions. But from the physical point of view, I would distinguish between the behavior of potentials according to the types of physics that you want to look at. So, for example, In the case of Wigner crystals that we was mentioning at the beginning, one has essentially a scale-free potential where just a Coulomb interaction is responsible for a transition between the superfluid to the Wigner crystal. Now, it turns out that when you have a multiple scale potential, then different types of phases can arise. And this is the case of the hard-soft corona, or the soft-soft, or the multi-soft potentials that are these Lifshitz-Patrick potentials that I was showing that were the objective of some recent investigations. So I would say it's most important, I would say from this perspective of crystallization, how many length scales do you have in the problem? And what are the ratio, or what are the typical energy scales associated to these length scales? Of course, one length scale which is very important is the average interparticle distance. Of course, if the average interparticle distance is very, very large, like in the case of ultra-cold atoms, typically in harmonic traps or in square or in box potentials, then there the details of the potential at very low, very small distance is essentially irrelevant. And that's why all these potentials that I was showing are basically giving you the same physics, which is the physics of a superfluid, just because the small distance behavior is essentially irrelevant. The story is different for the dipolar potential, because there you have also an anisotropy. So there it is the anisotropy that gives rise, and the fact that you have also a competition between repulsion and attraction that gives rise to droplets or supersolids that we know very well, right? But if you consider, for example, aligned dipoles in 2 dimensions, in purely 2 dimensions, then there you would have the transition to a Wigner crystal with single site occupancy. But this would take place at densities which are unrealistic for typical ultra-cold atomic experiments. So, for example, there it has not been realized Wigner crystallization. So the dipolar is what is peculiar, because you add other ingredients which are anisotropy and competing interactions. In our case, there is no competition in the signs, but there is the presence of multiple scales, and that's really the most important tool. If you now tell me, okay, look, I want to add a tail to these potentials, I can tell you quantitatively the physics could change. Qualitatively, I'm not so sure, because still we are interested at large, high densities, and therefore I would be mostly interested into the low, small, or actually the small distance behavior of the potential in order to find these exotic phases. Was it clear?
Yeah, very, very clear. But in your simulation, so you're considering, so there's no periodic boundary conditions, right? Because you said that it's a finite size in a way, or do
no, it's a finite, but still with periodic. So there is no external trapping potential. But it's periodic, but I mean, if one puts an external potential, then you would have a much more constrained system, and there very likely you would destroy quasicrystalline behavior.
Oh, I see. So for instance, if they, like Hazibavich has this very nice box potential, so in principle, yes, they could squeeze one direction and make your 2D system and maybe see quasicrystals.
You could then, I mean, in experiments, you can actually fill the system with very many particles. In our simulations, we have to do small system sizes because we have very small particle numbers that we can simulate, which is of the order of a few hundreds. If we go to a few tens of thousands and have actually an arbitrarily large or arbitrarily small or large box, then you could, in principle, even obtain this physics. I may be reluctant to say that it is immediate to find these phases just with a simple BC. You could, but you have to add some other ingredients in order to be able to obtain the precise parameter regime in order to obtain these multi-scale potentials.
Mm-hmm. Cool, cool. Thank you.
Are there other questions? Maybe I can say, I was curious, do you expect a fundamental difference between 2D and 3D systems? In general, does dimensionality, you expect a critical role?
Yeah, dimensionality can actually matter, can be relevant, but I would say in 3D, the physics might be much richer in terms of structures. So for example, if you just take the hard core potential, sorry, the soft core without this hard plus soft, just the soft, you can have that there are multiple configurations that can compete. Like for example, you have the BCC or the FCC periodic structures that have very close energy. Now, if you add the multi-scale, you can indeed show that we didn't do it because it's already quite complicated with the 2D. But people in the classical physics, so who are interested more in the physics of polymers or these other types of structures in soft matter, then what they did was to consider the generalization of this soft corona in 3 dimensions, and indeed you can find more complex quasicrystalline structures in 3D. And there the classification is much broader than what you have in 2 dimensions. But hopefully one can find this even in AMO systems. This would be, I would say, one medium, or maybe it's not so far in the future. But I mean, one needs really the proper ingredient in order to simulate these systems, I would say. And there are different ways to approach the problem. One is to look, as we did, to two-body interactions. Another possibility is to make some complex light coupling between the internal states, or using other physical other tools, like, for example, spin orbit effects in dipolar systems that basically give you, again, the competition between 2 length scales, one coming from the dipolar interaction when you have a confined system, and then the other one coming from the spin orbit. So again, the basic idea is to have competition between length scales. So I would say this is the most important ingredient.
And in AMO experiments, how much are they able to control the 2D nature of the system? I mean, to really confine particles in 2D. I mean, is it? It can
be done quite efficiently. It can be done quite efficiently. Yes. I would say that in our system, it's not really crucial to be exactly in 2D. The most important thing is that basically the transverse degrees of freedom are sufficiently frozen. But again, since we are talking about isotropic potentials, it's not an all repulsive. It's not like the case of the dipolar systems, where if we are talking about purely repulsive potentials, then even if it is quasi 2D, I would say that you are almost flexible with the dimensionality. So the most important thing is that you're looking at let's say, if you're looking at the system from above, and the system is not really moving a lot along the orthogonal directions.
Okay, so you're just in a strong confinement.
Yes, yeah.
Okay. Okay.
People, don't be shy. I know that here in Natal as well, people are a bit shy, but when I try to push them, they start to speak.
Doctor, this is a theoretical simulation which you show in this meeting. Is there any experimental done in this field? Did you compare this result, your result, with the experimental results which is reported in the literature?
So very good question. Indeed, indeed very good question. So what we have in mind typically are experiments with ultracold atoms. So by ultracold atom I mean either ultracold atom in their ground state that are usually studied in DCs, or polar molecules, or they can even be ions, or spin orbit coupled boson condensates, so, or even Rydberg atoms. So when you basically make a heavy use of the internal states of the system. Now, I think that he probably pushed on the wrong button, right? Because it disappeared. Right, Andre,
Oh, yeah.
Roman?
Yeah, I think maybe his internet just dropped. I don't know.
Okay.
Yeah, he's not here, but anyway, it will be recorded. So.
Okay.
Come back later.
No, but we have, I mean, yes. Okay, so the kind of experiments that we have in mind are these AMO platforms. As I mentioned, there are already some experiments that realize the quasicrystals, but in that case, the quasicrystalline symmetry was imposed externally. So this means that you have an external potential like a quasi-periodic potential in 1D or in 2 dimensions that give rise to the quasicrystalline physics. In our case, we were interested into the spontaneous breaking of the traditional symmetry, and that's the most important tool. For what concerns experiments in this direction, there are some possibilities by looking at in coupling between internal states of atoms that compose a BEC. From what instead is more interesting for us, which is the realization of these 2 body interaction potentials, I would say that probably the most promising direction is the one of Rydberg atoms, that by including dressing to probably many internal states, one can realize these multiple scale potentials. So I would say there are different avenues. There are some possibilities. Some of them have already been explored experimentally, but still there is a lot of work. I mean, there are several other possibilities that can be explored by experimentalists, and I hope that they will get interested by our proposal, of course.
Thank you, Victor. Thank you.
You will be able to get
You're
the full
welcome.
answer on YouTube later.
Got back.
Okay. Any more questions?
Oh, maybe a last one. So, Tommaso, so the quasicrystals, if you only have a mean field, you can still have a quasicrystal phase, right? You change only the symmetry that you get from quantum fluctuations, right? That's what's different from when you were showing the, yeah, and I didn't quite get it. So you have all the simulations at T equals 0. So some of them you've shown finite temperature, right? But in the T equals 0, you only find the 12-fold symmetry, right?
So the situation is the following. So when we apply this algorithm, this is intrinsically at finite temperature. But then, of course, you can reduce the temperature down to 0 temperature. There are other types of approaches, like, for example, variation Monte Carlo, diffusion Monte Carlo, that work precisely at 0 temperature. But nevertheless, even if you work at finite temperature and you reduce the temperature gradually, then you will stabilize the system and just look at quantum fluctuations, essentially. And thermal fluctuations are there because you intrinsically work at finite temperature, but it can be reduced arbitrarily because the temperature can be as small as you like. The comparison that I was doing, and I was mentioning that quantum fluctuations are relevant, it comes from the fact that if you apply a classical algorithm, which means basically classical metropolis algorithm to mimic the physics of a classical system, which was done, and it actually is being done to study the physics of these polymer systems in soft matter, etc. And you compare it with our simulation at the same values of the temperature, interaction potential, density, etc. In general, you will find a very similar phase diagram, but there are some regions of the parameter space where the configurations are different. And this is particularly interesting because it really shows that the quantumness of the system is relevant in this respect. For what concerns the quasicrystalline patterns, then we investigated very small, actually some specific cases, because to do these particular simulations is really heavy. So I would say this is the first attempt to address this problem quantum mechanically from really a microscopic point of view. But there are, of course, there can be other possibilities, of course. I mean, I think that in the future, if the other people want to tackle this problem and try to look at different type of quasicrystalline configurations, I think that there is space to do that, of course.